until we get to the very end. I will at the end, but all right. So first off, so exam 4. Remember that exam 4 is the take-home exam. So for this, from what we covered today until we get to, at least to the end, I'm hoping we get to the end of chapter 8. That'll be the material. I'll give it to you. You'll have a week to do it. You'll turn it in. It really shouldn't take you more than 2 or 3 hours to do. It's not something that you should spend like days and days and days on. And it will be everything that we've covered in class. So it won't be anything that you're like, we didn't talk about that. Okay? So the best thing for this is just try to make sure that you take the best notes possible. Try and write down examples. Try and like explain things out in your words, in your own words, or following along in the PowerPoints as we go, because those are what you're going to need to be able to answer these questions. Yep. It's, in fact, I have no rules. There's no rules except that I'm not going to tell you any answers. Okay? Yep. So, and like I said, you'll have an entire week. I'll give it to you. You'll have an entire week to do it. I will tell you that I've had people like not turn it in. I've had people turn it in and get a 99. I've had people turn it in and get a 50. Well, because you didn't spend any time on it. And you didn't actually take notes or pay attention in class. And then when you sit down to take it, you're like, I don't know how to do any of this. Well, it helps if you pay attention. It helps if you're here on time. It helps if you shut off your phone. It helps if you bring your notes. It helps if you actually pay attention. Like all of those things really, like taking college class really do help. You do better in school than the challenges. Okay. So starting from here. So last time when we quit, we were talking about polysaccharides, and we were specifically, I said, you can really split these huge carbohydrates into the digestible and the non-digestible types. So we talked about one of the digestible types. So we talked about the plant form, that's starch. Okay, so we already covered this. Remember, starch is really composed of 2 different molecules. There's amylose that looks like that long straight chain that forms that coil. If you were in lab yesterday when you had to do the test for starch, what's kind of interesting is when you add iodine actually fits into that coil that starch forms, and that's why it turned that blue-black color, like a real distinctive color change that occurs, and it's really that characteristic that creates that. So that's the starch, but remember, we can digest this. We talked a little bit about how in digestion that this takes hours to occur, but you do end up getting sugar because all of those little circles are all glucose. So all of these units are glucose units. We make an enzyme that can break all of these units into individual glucose units, which is why this, even if you eat pasta, bread, cereal, things that have starches in them, you are still going to end up having an effect on blood sugar. It just doesn't happen instantly. It ends up happening over hours of time. So then the second digestible polysaccharide is called glycogen. So glycogen is not made by plants. This is made by animals. So we're animals. Some people don't like to think of it that way, but you are. Okay? So being animals, we actually make glycogen. Rarely in your diet do you rely on glycogen as a major nutrient source. You do get a little bit if you're eating any kind of meat, just because there is glycogen that gets stored in muscles. So meat is actually skeletal muscle. The structure of glycogen looks just like one of the compounds that's in starch. So glycogen really looks just like amylopectin. And so amylopectin, remember I showed you here how amylopectin has that branched arrangement. So it's like chains of glucose with alpha 1 to 6 branches. So notice this branch. And then that can have a long chain, and there can be a branch off of that. So I think of it looking more tree-like, lots of sort of complex little ends to it, but still all just glucose. Just hundreds and hundreds of glucoses in this really big branched network. Well, glycogen looks like that too. but glycogen is actually even more branched. That's really the only difference between glycogen and amylopectin, is that the branches happen about every 12 glucoses. So if you're on the chain and there's 12 glucoses, then you're going to have a branch. Another 12 glucoses, another branch. And then those can have branches every 12. So you can end up with this really big branch structure. So I said glycogen's made by animals. The reason this is made by animals is this is your in-between meal. Glucose storage. So when you eat and your blood sugar begins to rise, what is the hormone that gets kicked out by the pancreas? Insulin. So blood sugar, so you eat, blood sugar starts to go up. When it gets above 110, insulin gets secreted by the pancreas, and that helps to bring it down, right? Because insulin is a signal to your body cells to take in blood sugar. Insulin also tells your liver and skeletal muscles, take extra sugar and store it as glycogen. So that in between meals, when are you not eating? Never. Huh?
When you sleep.
When you're sleeping, right? So for most people, the longest period of time that they go without eating is when they're asleep. So when you're asleep, your body is still needing glucose. It is still utilizing glucose. Your brain runs exclusively on glucose, and it doesn't even require insulin. So that means that your blood sugar, while you're sleeping, your blood sugar is going to decrease. So this is there as that storage form. So as your blood sugar drops, glycogen can get broken back down into glucose and help keep your blood sugar from going too low. So when your blood sugar gets around 60, now you can start breaking down glycogen, which then produces glucose. And that glucose gets put back into the blood to try and keep your blood sugar balanced. Because anybody has had bouts of hypoglycemia or low blood sugar knows like how crazy you start to feel, like how just sort of jittery and disoriented and shaky that you start to feel. Well, glycogen is there to stop that. Okay? Glycogen is there as that booster for blood sugar when you're not eating. So I think of it as my in-between meal glucose storage area. And it's pretty much liver and skeletal muscles, okay? Because the skeletal muscles, they can be very high in ATP or energy demand if you're exercising. So they may actually run out of glucose quickly. So you got glycogen already stored right there to be able to be broken down and shuttle glucose directly to those muscles to keep them being able to make ATP. Okay, so here's sort of the comparison. So notice just how similar these two are. So remember, these two are in starch. Flour, sugars, cookies, cakes, all of that. Anything with flour is going to have this these two compounds. But then glycogen, this is the one that is your blood sugar storage. But it's it's very similar to amylopectin. Just more branched. So when you eat, this gets bigger. So when you eat, glucose can be added to all of those ends. So you can end up adding. So glycogen after a big carb meal like spaghetti, glycogen can get bigger, okay? Because that's what your body is going to do, is store it. And then when you're sleeping, and your blood sugar starts to drop, now you can start clipping those glucoses off. So you can then break it back down, releasing that sugar into the blood to try and keep your blood sugar between 60 and 110. Remember, that's like that range that's considered like that normal blood sugar. So then the last one. So this is a non-digestible. So starch, amylose, amylopectin, and glycogen, you can break them down. You can actually make glycogen, but this you cannot, okay? This is fiber. Its technical name is cellulose. Cellulose has a different type of glycosidic bond. And so if you look at the one all the way down at the bottom, I tried to make this picture as big as possible. You might notice, I'm not sure, it might look a little different than what's in your picture, than your PowerPoint, because I tried to go back and make these a little bit bigger so you could see them. But looking at the bottom one, so the bottom one is actually a beta 1-4 glycosidic bond. So remember, beta, the angle goes up. And normally you would think of it looking like a diagonal shape. Remember, beta is the diagonal, whereas alpha makes the V. Well, in this one, you're like, well, it looks like an upside down V, then a backward, then a regular V, then an upside down. But if you look really closely at that first chain at the very bottom, the first glucose is oriented normal. So the oxygen's in the upper right corner. The second glucose is actually flipped upside down. Can you see that? So it looks like the oxygen's down below. So the molecules flip. The third glucose is back straight. The fourth is upside down. But by having this kind of flipped orientation, that beta 1-4 glycosidic bond makes a super straight line. So this does not form those coils like you see in starch. This makes a very straight line, and these can pack in really tight. Strands of cellulose can pack in, which is what you can see in that, like this middle area. The strands of cellulose pack in, forming very rigid structures. In fact, this is like an electron microscope view of cellulose. Can you see the strands? So it starts to look like thread. So cellulose fiber forms this very rigid arrangement. That is like what cotton, that's that top upper left, is like the cotton balls. So when you pick cotton, you know how it's all of these like thin strands that they then can make into thread and then make into clothing and such. So cellulose can be formed into a strand wrapped around, and it's really very strong. This is the reason why trees can be so tall, because the bark of trees, all of the plant cell walls are made of cellulose. So you can think of them as they make like little blocks that all can be stacked together, and they form this really rigid arrangement. So cellulose, the difference, beta 1-4. Alpha 1-4, alpha 1-6, those are in starch, those are in glycogen. We can digest those. We actually don't make an enzyme to be able to break down beta 1-4. Termites do, because termites eat wood, right? So termites will like eat the wood in your house. They'll eat the wood structures that help to support the house, and you have to like go tear all that out and put all new in. So termites actually have the ability to break down wood. We don't. Cellulose is sort of like wood fiber. So cellulose creates these really strong, rigid structures. We don't digest this. But some of the food that we eat actually contains fiber. So we don't necessarily eat like wood, although like bran flakes is not very far from it, okay? But when we eat fiber, we do ingest fiber. So remember in lab yesterday, and I tried to show everybody this in lab. In lab, we had potatoes, so we did an osmosis and diffusion lab. So potatoes, when you pick up a potato, it's all dry, right? But then we cut the potato, and the inside of the potato felt really what? Wet, right? Super wet. So it's all that moisture is contained within. So you're like, well, how come it doesn't dry out? That is because of fiber. So the cover on the potato is a fibrous cover that creates literally like a little waterproof jacket. It's the reason why the potato doesn't dry out. But now if you cut your potato and you just leave it, you'll notice the potato will start to sort of shrink and it'll get kind of mushy. It won't stay as firm. So it's why you always want to buy potatoes that don't look like they have any cuts in them, because they're going to go bad much faster that way. So the cover on the potato, the cover on an apple, okay, the cover on an orange, even like the crunchy part of like the reason why carrots are crunchy, celery is crunchy, broccoli is crunchy, like I'm talking about raw, or like if you lightly steam them, then they're still got like a crunch, they're still more solid. That is all because of fiber. So if you think of any of that crunchy vegetable and all the fruit covers, so all the fruit covers, all fiber. Like if you have coleslaw, the cabbage, almost all entirely fiber, okay? This is good though for two reasons, okay? There's two kinds. There is fiber that when you heat it, it does absorb some water, so they say it's soluble. So this means that it actually dissolves a little, and in fact, it'll make the food a little thicker. So for example, if you've ever had oatmeal, most people have had oatmeal. So you know oatmeal, like, yes, it has like the flakes of the oatmeal, but you know it has kind of like almost, I think of it almost kind of like this creamy kind of gravy kind of thing to it, okay? That's soluble fiber. So the only way you can make that out of oatmeal is you got to boil the oats. So the fiber in the oat flake absorbs a little bit of water, and that makes it, gives it that thicker texture. So that's always like the best example that I think of. Like refried beans, same, you notice how it has like a thick texture to it? That's because of soluble fiber. So, you know, like they mash, you take just black beans or kidney beans, you mash them. So that's going to give that same kind of texture. Cooked apples, if you ever had cooked apples, also almost kind of makes its own little like gravy kind of stuff in it. Some of that sugar, but some of it is actually fiber out of the apple itself. So those are just examples of things that have soluble fiber in them. Now, soluble fiber, one, when it gets in your stomach, it absorbs water, so it can actually make you feel full a little bit longer. So it doesn't take as much because it soaks up water as it passes through the GI tract. Also, because it does this, it's been shown to actually help slow sugar absorption. So having oatmeal, that's going to help if you put a little sugar, brown sugar on top of your oatmeal. Well, it's going to get absorbed a little bit slower. Also, it helps to slow cholesterol absorption. So somebody that has a high cholesterol that's trying to limit that, having a piece of bacon with your oatmeal, you're like, well, it'll just be absorbed a little slower. Not that it won't get absorbed, but it may be a little bit slower. Okay, so that's really the benefit of the soluble fiber. Insoluble fiber, though, is like the peel on an apple. Okay, no matter how you boil that, it's still going to be firm. It's still going to have some rough texture to it. Insoluble fiber doesn't get softer. It doesn't like what you see with the soluble type, but insoluble fiber is actually important because it has more of a laxative effect. So it helps to add bulk in your diet. So the thing to think about this as, large intestine, think of your GI tract. So you have your mouth, then the esophagus, then the stomach. A lot of digestion starts in the stomach, moves on into the small intestine. Pretty much in the small intestine, everything finishes getting broken down. All those, the sugars, the amino acids from proteins, fats, those get absorbed in the small intestine. By the time stuff gets to the large intestine, the last part of your GI tract, almost everything is absorbed. There's still a little bit of salt, there's still a little bit of water, and you have those bacteria that live in the large intestine that actually make a couple of vitamins for you. So they're helpful and beneficial. So the large intestine has its place. It's about the last 4 feet. The only way that the large intestine gets triggered, though, is by having something in it. So if the large intestine, if nothing comes into the large intestine, then it actually stays pretty quiet. So it doesn't contract as much. It doesn't move things along. So now you got to think, okay, so I've absorbed sugars, I've absorbed proteins, I've absorbed fats. What else is there in food? So some water gets absorbed out of the large intestine. A lot of it got absorbed along the way, but so water absorption happens in the large intestine. Some salts get absorbed. What else is in your food? Carbs. Carbs got absorbed. Okay, right? Sugars can get absorbed through your mouth. Starches get digested and absorbed in the small intestine. Proteins get broken down in the stomach, absorbed in the small intestine. Fats get mixed in the small intestine and absorbed. So those nutrients are already absorbed. So what ends up landing in the large intestine? What else is in your food? What's in the Mountain Dew? Calories are all from nutrients. Those are all get absorbed. So caffeine is one. So caffeine does get absorbed. That's why you get like, that's what like the stimulant effect. It does get absorbed. What else is in there? Keep reading. Those little,
Sodium.
that gets absorbed. That's a salt. Keep reading.
How about carbohydrates?
Carbohydrates get absorbed. Look at the ingredients list. Go down to the fun part. Can you read any of those? Those really long words.
like so intrigued.
Huh?
That's what I'm like so intrigued. I don't know.
So in here, you've got,
She may know more than her.
all right, so there's sodium citrate, there's gum arabic, there's erythrosorbic acid, which is a preservative, okay? Calcium disodium ETA to protect flavors. Yellow number 5. Are any of those nutrients?
No.
None. None of them are carbohydrates. None of them are proteins. None of them are fats. They are all preservatives. They are flavorings. They are colorings, okay? You didn't absorb any of that. So where does that go? Into the large intestine, okay? So you got these little chemicals that don't get absorbed. They have no purpose in the body, but they're added as a flavoring, as a coloring, and added as a preservative. If there's no fiber in your diet, then those chemicals stay in the large intestine. Because I told you the large intestine doesn't really do its little contractile moving unless there's something in there. Those chemicals are really small. They're not going to create or stimulate the large intestine to move. So if they just stay and hang on or lay up on the wall of the large intestine, over time, what can they do? They could cause irritation. Okay, so having these artificial colors, flavors, preservatives, they could cause irritation on the wall of the large intestine. And what is something that the large intestine will form? People oftentimes have to have these removed during a colonoscopy. A polyp. Okay, so a polyp is almost looks like a mole. Okay, so like you've had a mole on your body. Okay, it's just like a little nub. So your large intestine is about this big in diameter. What happens when you start to get a mole, a polyp? It can get big enough that it can actually create a blockage. Sometimes polyps, though, with irritation, can actually start to form abnormal cells. Abnormal cells can develop into cancer. And then, because this is a very vascular tube, there's lots of blood vessels that are not on the wall, but just in the underlying layer. That means if you have abnormal cells and a lot of blood vessels, those abnormal cells then can move. So then they can spread and go to other organs.
So I know that like Mountain Dew's been banned in other places. Can it cause?
So Mountain Dew is one that there's a high correlation to kidney stones. Not gonna lie, if you've ever had a kidney stone,
my
like,
sister-in-law has them right now, and oh my god, she was up like the past 3 nights crying till like 3 a.m.
it is like worse than labor pains.
And hers
it is just
aren't even like huge ones either. They're
yeah,
like just above,
well, that's because
like,
you're
going
passing
through a
something
colander.
that's this big, but you're passing it through a tube that's 10 times smaller.
Yeah,
and this is sharp. It's like little sharp
like
rocks. It's not fun, but this is the reason why the increasing any kind of fiber in your diet, that means even the soluble fiber, it all ends up getting into the large intestine. That stretches the walls of the large intestine and stimulates movement. So that you can kind of think all this other junk that you eat, stuff that's not absorbed, stuff that's not digested, stuff really that has no nutritional value for you. Adding fiber to your diet helps to move those things along so that they don't lay on the wall of the large intestine and potentially cause problem down the line. So that's why they say adding fiber to your diet reduces your risk of colon cancer. So the colon is just a generic name for your large intestine. Okay? Colon is the same thing. Okay? The colon, the large intestine, they're really both the same. So that's the reason. That's the reason why. And so just keeping that in mind, and like your diet, a lot of the Eastern North Carolina diet is very low in fiber. Very low in fiber. French fries, not a lot of fiber. Fried chicken, not a lot of fiber. Barbecue, not a lot of fiber. Pretty much if you go to a barbecue place, the coleslaw, you get some from the coleslaw and maybe from the hush puppies, but not very much. Okay, so all the ones you see, whole grains, seeds, brown rice, the vegetable skins, okay, like eating the skin of the potato, not just the inside. That's like, because even when you get the boiled potatoes at Parker's, they've already been skinned, right? There's no skin on them. So you're like, well, you just took all the fiber right out of that. Like, we're just going to give you the starchy insides. Here you go. Yeah. So just keeping that in mind, especially if this runs in the family, because there is a genetic connection with colon cancer as well. So that's where increasing and trying to make sure that you're having bowel movements on a regular basis, like at least every other day is considered normal. Less than that really means that those chemicals that you're ingesting, beside the nutrients, that stuff's hanging out in your large intestine. So that just increases that risk.
So like fruits and stuff aren't the ones that move?
Yeah. So like, okay, so if you think of an orange, so the segment of the orange, that is all the fiber. Okay. So, like how if you break an orange and you split it into slices, the cover that holds the little orange pieces together, that's all fiber.
The white pieces are?
Mm-hmm.
Okay.
Okay. You don't have to eat the peel because it's pretty bitter. Okay. But I'm talking about like the part inside. So the problem is when you make juice, what do you leave behind? You leave all the fiber behind. You only get just the sugar water. Juices are terrible because it's nothing but sugar and water. Okay? Yeah, you are so much better off eating the fruit because you're going to get the fiber. When you make juices, you get rid of all the fiber. It all gets filtered out because people are like, oh, I don't like that. I'd just rather drink this. It's very sweet because they do that and then they add sugar to it. Yeah. So that's where, so whole fruits, whole vegetables, not cooking vegetables to death. And I will tell you, my mother was one that was like, yeah, we'll make you some Brussels sprouts. And it'd be like mushy.
Yeah.
It was like, we were all like, we don't like this. And then I grew up and I was like, oh, you can like broil them and they're like a little charred, but they're still kind of crispy. And I'm like, I like them like this. That's not how my mother cooked them. But yes, that's like definitely any kind of cabbage is fair game. Cabbage is like full of it. All right. So there's just the reminder. So amylose and amylopectin, those both come from plants. Those are your starches. But the bottom one, cellulose, which is fiber, also from a plant, but that's not the digestible. Cellulose is equal to fiber. Same thing. Okay. Cellulose is its technical plant name. Fiber is what we call it in terms of our diet. Because when you talk about cellulose and you think of wood, and people are like, I don't eat wood. Well, you sort of do. You eat woody stuff if you eat any plants. Last topic in chapter 6 is about your ABO blood group type. So maybe you know your blood type. Maybe you know if you're type A, type B, type O, or maybe you're AB. That's kind of the more rare one out there. Most common blood types are type O and type A. Okay. They do vary by racial areas just because of where people used to live, right? Used to live in the village and never go anywhere. So everybody in your village are married and so you all had the same blood type, right? Mm-hmm. Well, like Native Americans. So I just know like my mother's Native American. Everybody in that side of the family, everybody's type O. And that is like 90% of Native Americans are type O because we lived over here before any of you people came. And that's why, like, so therefore, if there were like a few and then they had lots of kids and everything, so they all ended up having the same blood type. So different areas tend to have differences in terms of like abundance of A versus B versus O and AB. But most in the United States, most common is A and O, okay, by far. So that makes up like 60-70% is A and O. The other two are much less common. But what does that mean? So what this is really referring to is this is actually talking about the pattern of sugars on the surface of a red blood cell. So remember, so your blood cells carry oxygen, that's their job. But they found that somebody lost a lot of blood and they needed blood. They were like, okay, well, we're going to give this person blood. So we'll insert a needle and drain it from this person and then put it into that person. And sometimes that works really well and the person survived and then sometimes they died. So then they were like, I wonder why that happened. Sometimes it was you had better luck if you gave blood from like a parent to a child. Sometimes that didn't matter either. So there was this question of why is it sometimes if you give blood from one person to another, it gets rejected. And rejected means that your immune cells actually attack and destroy the blood that you're given. And sometimes you don't. Sometimes it's fine. Sometimes it's accepted. So it led to this understanding of the ABO blood group types. So here are the 4 possible sugars. Really only one of them you've actually heard of, galactose, right? So you've seen galactose, it's part of milk sugar. So there's 3 others. There's fucose, and you don't have to remember the names of them. There's fucose, there's N-acetylglucosamine, and N-acetylgalactosamine. The only difference on those bottom ones, do you see that they have an amide? There's a nitrogen, carbon, double bond oxygen hanging down. So that kind of makes them look a little strange, a little different than the normal sugars we've talked about. But these 4 sugars, they form a pattern. So if you're type O, here's the little type O red blood cell. This means hanging off of the type O red blood cell, they have this 3 sugar pattern. So there is the one that is kind of like that light purple, the orange, and the yellow. Like you don't even have to really remember the names. Just remember, so there's this 3 sugar pattern on type O. Now, compare that pattern to type A and type B. They all have something different hanging off, but do you see that they all have the same 3 that O has? They all have that light purple, orange, yellow. So type O has a pattern that is part of all the other blood types. So you can take type O. If you give type O to type A, do you see that type A would see those 3 as being something that's normally there? Okay, that 3 sugar pattern is found in all of the blood types. So type O can be given to anybody because it has the same 3 that wouldn't be recognized as foreign. So if I took type O blood and gave it to type B, the type O blood would not react with type B. Even though type B has that extra one, that basic 3 pattern is seen as kind of normal. It's present in all of the different blood types. So type O has that 3 sugar pattern found in all blood types. And this is why it is the universal, if it can be given to anybody, it's the universal donor.
Is that a positive and a negative?
So positive and negative is a completely different thing. It's not part of the ABO. So positive and negative, and I'll explain that a little bit. But first, just this, like just the letter, not positive or negative. If you're type A, it can be positive or negative, but it doesn't change what this pattern is. But now here's the rub. If you're type A and you give your blood to type O, is it going to look the same? No. So if I'm type A and I give it to type O, then that 4th sugar, that one sticking up, type O immune system's going to go, no, that shouldn't be here. That's foreign. Attack it and destroy it. And so you are automatically, like within weeks of birth, you become immune to any foreign blood cells. Yep. I'm type O positive. Yeah. So O positive. And so being type O, the Red Cross calls me constantly because you can get, yes, every day, texts, good grief. Yes. We'll give you a t-shirt. I don't care. Okay, I ain't got time right now. So, but the universal donor, because it's that generic 3 sugar pattern, you can give it to anybody. But A, I can't give to O. Now, can I take A and give it to B? Would it? No, because it's different. It does have 4 sugars, but it's a different pattern. So it has to match whatever blood you're giving to somebody. It has to match, or at least have the basic pattern that receiving blood has. So A can't give to B, A cannot give to O. What about B? B can't give to A, B can't give to O. So there's a 4th blood type we haven't talked about. What's that? So type AB has both of these. So that means their red blood cell has this pattern of 4 and this pattern of 4. So it's got both of those patterns. So if I'm type A, can I give to AB? Yes, because AB has A. So AB can get type A. Can I give B to AB? Yep, because they have the B pattern. And it's not a problem if they're missing the A pattern as long as they don't have something that's foreign, that doesn't blend. Can I give O to AB? Yep, because that's a universal donor. You can give O to anybody. So I can give all of these. That's why they call AB the universal receiver. Okay, so AB has all the patterns, so nothing is foreign to them. So you're super lucky if you're AB because they can give you anything. Doesn't matter. But if you're type O, you can't get anything but O because type O has kind of like the simplest pattern. So anything with more sugars is not going to work. So I can't give A, B, or AB to O. I can only give O to O.
Is your whole family O?
Yes.
Because my whole family's O.
Mm-hmm. Yep. Yep. And that's, I mean, my daughters are too, but that's because their dad was O. so we're all just this whole family of O's. And I don't really know about my brother's wives because that can like introduce differences. It's all genetic combinations.
How does it work sometimes when a woman gets pregnant that a baby has a different blood type than the mother?
Okay, hold on. Okay, so think AB has all the possible sugar patterns. Nothing is foreign to AB. Okay, but like A, I can only give A or O to type A. I can't give B, I can't give AB because that would have any Bs. Like A can't get anything with a B, B can't get anything with an A, right? So B can get O, B can get B, AB can get anything, and O can only get O. But it's really because of this. It's the sugar pattern that creates this, and your immune system actually recognizes that pattern and says, okay, this is part of us. This is me. And so anything that comes in that's foreign, your immune system will attack and destroy it. So you have roughly 5 to 6 quarts of blood in your body, depends on your size, right? So like Ari's not going to have that much. Okay, I have more. So it all has to do with size too, right? So average females are 4 to 5 liters, males are 5 to 6 liters, so average about 5. So it's like kind of like 5 quarts, almost over a gallon. If you get more than 20% of this mismatched blood, your immune cells will attack and destroy those transfused blood cells, and that can cause permanent damage to liver and kidney.
Or even if it's one that you can have?
If it's one you can have, you're fine. But like if I'm type O and they give me A blood, if they transfuse more than 20% of my blood supply, that, because your liver and your kidneys are filters, right? So their job is to filter stuff out. Your liver and your kidneys can end up having irreversible damage. And that can cause death. Like that can cause shutdown, loss of those organs. So there's a couple of criteria. So one, if you don't weigh, I think it's like 100 pounds.
It's like 100. I can't give it. I'm like 100.
Yeah, and it's because of your blood volume. They don't want to take too much because that could make you anemic. Okay, that would drop. And they also, even if you're over that weight, they're going to check your blood to make sure you have enough red blood cells to make sure you're not anemic. They don't want to take blood from you if you're anemic because anemic means you don't have enough red blood cells already. So if we take, then we're going to make you even more anemic. So we don't want you to like stand up and fall down. Okay, so that's like the most common reasons that you end up not being able to donate. Females have a much bigger issue because of menstruation. So your amount of red blood cells varies according to your cycle. So like sometimes you can give blood if you haven't had your period, but after your period, you actually might be borderline anemic. And so then you're not eligible. So there's some people who are like, sometimes I can, sometimes I can't. It really just depends. They're like right on that line in between. So that's typically why. So last question. So here's the information more about universal receivers and donors. So the last question someone asked is about this plus and minus. So I'm O positive, okay? You might be A negative. So, okay, More people are positive. Negative is a little less common, but the positive and negative, for example, O plus or O negative, that is nothing to do with the ABO. It does not mean anything about those sugar patterns. ABO is purely those sugar patterns. The plus and the minus are referring to if you have a protein on the red blood cell that they named RH. They named it because it was first discovered in rhesus monkeys, which is why it ended up being RH. So that's why they get these random names. Okay? So if you're RH positive, then whatever blood type you are, you put a plus after. Okay? If you're negative, it means you don't have it. So this is no RH protein. And this actually has less of an issue in a transfusion. So if you are O negative and they give you O positive blood, that's not going to be devastating to you. The problem really comes into play if you're RH negative, so if you're A negative, B negative, AB negative, O negative, if you have a negative blood type, that means you don't have that RH protein. The first time you are exposed to that RH protein, like say they gave you a transfusion of RH positive blood, the first time you have an immune response. So now you become immune to RH proteins. So if you ever come in contact with blood that's RH positive again, your immune system will attack it. Okay? So it doesn't happen the first time, it's always the second time that you become exposed. So this became a big issue in pregnancy. I think I spelled that right. Just looks strange. Okay, I was like, Nancy. That's just like, all right. So in pregnancy, if you're an RH negative mother, that means that you don't have the RH proteins. But if dad is RH positive, there's a chance your baby is RH positive. So if you have an RH positive baby, now during labor and delivery, when baby is born, the placenta, which was like tightly like enmeshed with the uterus, that was how baby was getting its oxygen and nutrients for those 9 months. But during delivery, that pulls away. Okay? When it pulls away, there's a mixing of mom's blood and baby's blood. This is a good thing for baby because mom gives like antibodies, mom gives like this newborn sort of this boost that helps to protect them until their immune system really gets rolling. But on the negative part, mom's blood, if baby's blood gets into mom's bloodstream, RH positive is exposed to the RH negative mother, she has an immune response. First baby is born fine. But now, mom's immune to Rh proteins. So second baby that's Rh positive, what can happen?
The mom could die.
Miscarriage. So this can actually, like the little, for us, the second, doesn't happen in the first pregnancy. The first pregnancy is when this becomes like, you become immune. You become what they call sensitized. So your immune system like says, Rh proteins are foreign. We shouldn't allow them here ever again. And so the second baby that's Rh positive, that can cause baby to be attacked. This worst case scenario, miscarriage. And maybe, and this used to be a bigger issue like earlier 1900s, and maybe you knew family members where they had one child and never could have another child. She just miscarried every other time. That could have been the possible reason. So that first pregnancy, they figured out that this was caused by this Rh protein, which is the reason that you used to actually have blood tests done. Before you could get married, you used to have a blood test done.
Wow.
One of the things they would do is test you for Rh. They'd also test you for syphilis. They would also test you for some of the other STDs so that you knew what you're getting into.
It's like, hold on, you can't get married yet.
Huh?
They should still do that.
Huh?
They should still do that.
Yeah, they stopped because they were like, no, that's not, shouldn't be. But that up until like 1950, you wanted to get married, you had to go and have a blood test done. Because one thing they would test you for is Rh, because they knew there was this issue. Okay? So they would like caution you, if you're Rh negative, Marrying an Rh positive person, like this can happen. This could be an issue. Now, if all your babies are Rh negative, if like your gene holds and all your babies are Rh negative, not a problem. Only happens with an Rh positive baby and an Rh negative mom. So if you get blood typed, and now if you go in for prenatal care, one of the first things they do test you for STDs. Another thing that they're going to do is they are going to blood type you. Because if you're Rh negative as a pregnant female, they will give you what's called Rogam. It's a shot. Used to have to do 3. Now I think they can just do 1. So when you go in to deliver, you get a Rogam shot, and that blocks your immune response. So it keeps your immune system from becoming sensitive to Rh proteins.
So if you got like an Rh positive dad and Rh positive mom, then it's
No
fine.
problem.
And if you got an Rh
Only if
negative-
mom is Rh negative. This is the only scenario that you could end up with hemolytic disease of the newborn, is what they call it.
That's the fix now, right?
But yeah, now it's not an issue. But it is the reason why you get prenatal care, and they do blood typing to see if you're Rh negative. And they don't even blood type dad because, like the mailman could be dad. Like you don't always know. So they don't even care what your blood type, what dad's blood type. They're just like, you're the mom and you're pregnant and you're Rh negative, you're getting a Rogam shot. Okay? Even if dad's Rh negative. Well, because of, this could have some serious consequences.
So they don't test the baby to see if you even need
Nope, they don't even care. They're just going to do that. So they're just going to do that because it's preventative. Okay? And it's not something, it's only going to last for a short period of time. All it really does is block your immune system cells from reacting to this exposure to Rh proteins.
And it lasts all birth.
Huh? No, they don't give it to you until birth. They give it to you because it's at birth when the placenta and the uterus separate. That's when blood gets mixed. So that's when they give you the shot. So then that lasts for a couple of weeks. And in that period of time, those Rh red blood cells, those just get filtered out like normal because normal red blood cells, they get older, they get filtered out. And so they won't be in your blood system for a long time, but they're going to give you one that's going to last a period of time to block that. That's really what the positive and negative are. Okay? That's really, huh?
It can't happen the other way, like if the mom is positive and then the baby's negative.
No, because baby doesn't have a functioning immune system yet, right? Because at birth, their immune system is still like, what? Where are we? What? Yeah. Huh? What? Yeah. They're still like, that's why. But that's why that mixing is good for baby because some of mom's antibodies actually get transferred to baby and gives baby some protection. Colostrum, like that first breast milk, also gives more protection. So they kind of get like this little boost that lasts a couple of months because it does take their immune system a while to start like recognizing self, foreign, what's right, what's wrong, and then start to respond to things. Okay? But that's the reason that comes into play. All right, so that finishes 6, and it kicks me off, but that's okay. Okay. So again, just as a reminder, so exam 4 is a take-home exam. It will cover that very end of 6, all of 7 and 8, and we will see how far we get into 9. Sometimes I just cover like the background stuff of acids and bases. Sometimes they get further along. I'm guessing that I'll be happy if we get through 7 and 8. Okay, so like I said with this, I have had people get hundreds on this. I've had people get zeros because they didn't turn it in. And then I've had people that got a 50. The kicker in this is you really want to make sure that you take notes. You really want to make sure that you're going through and writing down examples, doing steps along the way. Because if you do this, when you go to take this take-home exam, all the questions we've covered in class. Okay? So all the questions we've covered, if there's math, it's going to be just like some of the ones we did as examples. So if you don't write any of it down and you get home and you get a take-home exam, you're not going to know what you're doing, okay? So you're not going to be able to figure it out. If you have a challenge following the steps of the math, we will go through each one, okay? So the very beginning of this chapter 7 is really looking at what they call intermolecular forces. So this is like when molecules are attracted to each other, like the why behind it, So gases are covered first because gases don't care about each other. Gases don't do anything with other gases. Gases are sort of their own state of matter because they are extremely far apart from each other. So if you think about the air in this room, the gas molecules are like, wah, 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 wah. Okay? They really rarely even touch. They're so small and there's so much empty space between molecules that they're in this constant motion. So gas molecules don't just sit still. They're like constantly floating around. So when you're doing like this, like you just cause them flinging them from one place to another. It's sort of kind of a weird thing to even think about. But because they're so far apart, they have no attractive force to each other. So if two molecules come near, they're not going to like stick together. They're just going to like move along. So there's really no attraction. I always think like it's sort of like plastic. No attraction at all. Okay. Gases don't have any kind of attractive force that holds them together. That's why they can spread out in whatever space you give them. They're constantly moving. So that means that they have kinetic energy, right? Because that's that energy of motion. And it's completely related to their temperature. So remember that temperature, I said, is like the vibrational activity that a molecule has. When you like boil water, you watch that liquid and you can see that it starts to move. You can see sort of swirling patterns in the liquid. And then you see bubbles start to form. It gets more and more vigorous in terms of the liquid movement. So same thing, but gases are even more so. So gases have this vibrational energy. And if you increase their temperature, they're going to vibrate more. So what do you think that'll do to their movement? Think they'll move faster or slower? Faster. Heat them up, they're going to move faster. You cool them down, they're going to move slower. So if they vibrate slower, they're not going to be moving quite as fast. So cold air versus warm air. Warm air, those molecules are moving faster. So just remember, it's completely related to temperature. So knowing these things, there were scientists that studied just gases, like their entire life studied just gases and the behaviors that they have. There are characteristics of gases that you can define that's a little different than solids and liquids. So because gases fill up this space, I can take gases and I can change the size of their space. I can't really do that with a liquid and a solid. Like you can't take this desk and squeeze it into a smaller space, right? You'd have to crush it. Like I couldn't keep it that size and squeeze it because solids are so tightly, those molecules are already so tightly compact. But I can do that with gases because gases, see if I can draw dots. 1, 2, 3, 4, 5, 6, 7, 8. So like I can have gases like this, or I could take those gases. That's 9. And I can like squeeze them into this smaller space. They're still not touching, okay? But now, if I do this, these gas molecules are moving. Which one would you expect to bounce off the walls more? The bigger one or the smaller? The smaller. And that creates pressure. So pressure is the force of gas molecules bouncing off the walls of their container. So the smaller the space you cram them in, the higher the pressure. It's just this force exerted on a given area. So this smaller space with the same number of gas molecules, they would bounce off the walls more, higher pressure. 2 units of pressure to recognize. 1, atmosphere. Okay, so if you see ATM, that is the abbreviation for pressure, atmospheres. The other one is mmHg, which stands for millimeters of mercury. So if you see atmospheres, or if you see mmHg, millimeters of mercury, those are both common pressure units. So sometimes making sure you can recognize, okay, what does this unit mean? What does this unit? Like if you see volume, what is the common unit? Liters, okay? So for volume, it's going to be liters, but pressure, it's going to be atmospheres or mmHg, either one of those. Now, maybe you've heard mmHg when thinking about blood pressure. Okay, so blood pressure is really not a gas pressure though. Blood pressure is measuring the pressure of the blood on the walls of the blood vessel. Typically, it's in your arteries. So that's where the blood pressure cuff is put on that brachial artery. But it's still, like the perfect blood pressure is, I used to call it, that's the blue book value, right? The gold standard. I don't know how many of your patients have ever had of 120/80, but 120/80, both of those units are actually millimeters of mercury. So they would both be mmHg, mmHg. We're notorious for just dropping those units off, like blood sugar. My blood sugar is 100. Well, it's 100 milligrams per deciliter of blood. But those health people just drop the unit values off and just give the number value. But that's really what that's talking about. It's talking about the pressure of the blood on the walls of the blood vessels. The top number is the highest pressure. The bottom number is the lowest pressure. So it kind of gives you that range. Now, you might also see things like this, but we're really not going to use these. Pounds per square inch, if you pump up a tire, has anybody ever had one of those little tire pressure gauges? Yes, especially driving the old car. You're like, uh-oh. All right, happens a lot. You're like, that looks a little low. All right, so that's pounds per square inch. So that is saying like how many pounds of force or pressure per square inch on the wall of the tire. So that's what that means. And so there you fill it up to 35, 32, whatever the range is for your tire. But we don't really use that in chemistry and calculations. Last one, the SI unit, the Pascal, that's way more of a physics unit that is commonly used. So for me, atmospheres and millimeters of mercury, those are going to be the ones that you're commonly going to see. So, Dr. Boyle. So remember we talked about radiation chemistry and I said this happened like right around the end of the 1900s. So this was like 1880, 1890, right around the year 1900 was when radiation was really starting to being understood with Curie and Becquerel. This is like 300 years before that. So this was in the 1600s. So understanding of gases was the research and the experiments that were done was quite a long time ago, but they've actually still all held true. So this chemist, Robert Boyle, he looked at what happens to gases if you change their volume and their pressure, but you keep the temperature the same. So he did all of his experiments without changing temperature. So he kept them all like either at room temperature or kept them all at 100 degrees. He kept them all at the same temperature. He found, and for the first example, so we'll say this is the initial experiment. So he had a syringe and see the little marks. So we'll say each one of those marks is like a unit of volume. So that's one volume, and one volume. So that would mean it has what? 3. Right? So there has 3 volumes. Each little increment we'll just say is 1. Maybe it's a mil, maybe it's a cubic centimeter. We'll just say it's 1 each. So there's 3. 3 little notches there. I'm trying to spell right. And then this position, he's not pushing down. The syringe is just like stuck in there. So there's a cap on the end so that you can't just push it out. So it's like now this gas is trapped in this syringe. So he said, if I put twice the amount of pressure, so instead of it just sitting there, I'm pushing down twice as hard as the first one, what happened to the volume? So if this is 1 pressure, this is going to be double the pressure. What happens to the volume? It goes down to what? Like how many notches would you call that? 1.5? Mm-hmm. So I started off with a single pressure. I have 3 notches on the volume of the syringe, but if I double the pressure, the volume goes into half of its normal size. And then the next one, if I have 3 times the amount of pressure, how many volume units do I have now? Only 1. So can you see that 1 times 3 is 3. 2 times 1.5 is 2 times 1.5? 2 times 1.5? No, 1.5 plus 1.5 would be 3. And then 3 times 1, 3. So all of those, do you see that their ratio, the pressure times the volume, that as I change the pressure, the volume changes to correspond so that all three of those examples, if I multiply pressure times volume, I get 3. 1 times 3, 3. 3 times 1, 3. 2 times 1.5 is also 3. So we said there's a proportion. There's a ratio. If I change pressure, I change volume. If I increase the pressure, what does that do to the volume in this? Does it go up or down? Down. Also, if I took and I increased the volume, what do you think that would do to the pressure then? Decrease. So he came up with this and said, hey, pressure and volume are inversely proportional. If one goes up, the other goes down. So inversely proportional means that they change in opposite directions. So the best example of this, common example, is breathing. Okay? So here's where if you've had the A and P, then this is like, oh, this totally makes sense. Totally am with you. If not, just listen. Okay? Breathing is all because of pressure and volume changes. Your lungs are basically like elastic balloons that cannot inflate themselves. The only reason that your lungs inflate is because of changes in your thoracic cavity. And the changes affect the volume, which then affects the pressure. So think like sit for a minute, do a normal exhale. Now when you do an inhale, can you feel that your chest feels like it goes up? Now if you do a deep breath, you can really feel it, right? You can like really try to expand the ribs. But if you just like take a normal breath, you can feel your ribs rise just a little bit, okay? The chest goes up just a little bit. Those muscles that do that are right between your ribs. They're called the intercostals, which means between the ribs, okay? So the external intercostals, their job, they pull your ribs up and out. So when you inhale, those ribs come up and out. That is this. So out, out, out. So your thoracic cavity, nice and flexible, not so much when you're old, but nice and flexible. The diaphragm is the other muscle that comes into play. So your diaphragm is the muscle that splits your thoracic and abdominal pelvic cavities. So it is this sort of circular flat muscle that spans right here. And it actually separates these into 2 separate cavities. So normally your diaphragm at the end of an exhale, when you're like down there, that's when that diaphragm is relaxed. And when a muscle relaxes, it gets longer, right? Because when you contract the muscle, it gets shorter. When you relax the muscle, it gets longer. So when the diaphragm is relaxed, it's more domed. So it kind of has this dome shape. But then when it contracts, it goes like this. Do you see this is shorter than this? So when the muscle contracts, the diaphragm actually goes down. So that is this one. Diaphragm goes down, diaphragm goes down. And you don't really feel it. If you've ever had a kid, like when you're like late pregnancy, this is where you're like, I can't take a deep breath anymore. And that's because baby's way up here. And so your poor diaphragm's like, your diaphragm like can't push down enough to actually try to inflate the lungs. That's why you're like, okay, I can breathe like that. But yeah, when you're sitting like this, you're like, I can't hardly breathe. So this might look a little extreme. But here, can you see thoracic cavity goes up and out? Diaphragm drops down. What does that do to the volume? Look at the one versus this one. Volume goes up. Does everybody agree? The volume inside. So we have an increase in volume. So increase in volume does what to pressure? Decreases, right? So we said, Boyle's law said, if the volume goes up, that's going to create a drop in pressure. In fact, that is called negative pressure. So the pressure now inside of your thoracic cavity is less than the pressure outside. Negative pressure is suction. So if you like don't allow air in, but you try to do an inhale, it feels very strange. right? So you start trying to inhale, but don't allow air to go in. You can almost feel like your neck feels like it goes, like it feels like it's getting pulled down into your chest. That's that negative pressure, okay? So you want to balance the pressure. To balance the pressure, what do you allow to come in? If I have suction, I allow air to flow in, and what does that do to the pressure? Balances it out. So increase in volume decreases pressure, air gets sucked in. So your lungs just stretch. That's all they do. So the lungs are really just filling with air to try and balance the pressure that's inside of the thoracic cavity. So now I'm at the top of the inhale. And now I'm going to do the exhale. So inhaling is always called, this is an active process. It's active because it requires contraction. Muscle contraction is necessary for inhaling to occur. This is why people that got polio actually paralyzes the nerves that stimulate the respiratory muscles. So they ended up being in like an iron lung because the respiratory muscles didn't work anymore. Exhaling, though, passive. And if you watch anybody sleeping, especially those snorers, okay, that's like I have a pug mutt, and like she snores like a little old man, like in the middle of the night. I like shake her. Stop it. she'll get her head all twisted, all crazy, and she makes so much noise. I have some recorded videos during COVID, and students were like, "What was that noise in the video?" It was my dog. I swear I wasn't snoring and teaching at the same time. But you can hear her in the background. She gets very relaxed. But when she exhales, no noise, because exhaling is when muscles relax. So when muscles relax, the external intercostals stop contracting. So now automatically the ribs start coming in and down. The diaphragm relaxes, which means that it's going to start to rise. So it's going to go from its contracted state and then going to bounce back up. So it's going to have more of a dome arrangement. So now it goes back to this. It's a terrible looking thoracic. Okay, so what does that do to the volume? Now I decrease the volume. And if I decrease the volume, what does that do to pressure? Right? If I decrease the volume, I increase the pressure. So now there's force like a balloon. There's force inside of that balloon. What happens when you let go of the end of the balloon? Right? So all that air just flows out. So that's how you rebalance that pressure. So decreasing the volume, increasing the pressure, that is going to push air out. And the lungs deflate. Like balloons. Just think of them like balloons. Yeah. So then once you decrease the volume, that increases the pressure, and that is the force that helps to push air out. And you start it all over again. Okay? So ventilation, this is called ventilation. This is the physical act of moving air in and out of the lungs. This is entirely because of pressure and volume changes. Mm-hmm.
Was the inhalation where the diaphragm is not flat, or was it the
Inhalation, so like when you think of the diaphragm, because it's kind of a weird muscle to think of because it's like it's a round flat muscle, okay? And so when it's relaxed, it's longer. That's why it's domed, okay? When it contracts, it gets flatter. So it actually drops down. So you can see like this looks shorter than this. So this is a longer span than when you have it flattened. So that's relaxed, that's contracted. And it's weird because you always just think of your biceps, like which is like just does this. But this being this kind of flat muscle, when it contracts, it pulls itself down. When it relaxes, it bounces back up. Yeah, maybe I didn't make this bounce up quite as much as it should. Okay, so Boyle studied all of this and said, okay, there is an inverse proportion between volume and pressure. So I know that if one goes up, the other is going to go down. And vice versa. If one goes down, the other goes up. Right? So one goes up, that's that inverse. So just remember they should go the opposite. In fact, so if I know the condition of pressure and volume on a sample of gas, I can figure out what the pressure and volume on that sample of gas is if I change one of the criteria. So they call this PI, which is the initial. I'm more of a P1, V1 person, so that's just me. So I think of P1 as being the initial pressure, V1 is the initial volume. What's a P? And it should be equal to and proportional to the pressure and the volume after we've made changes. So part of this is understanding how to rearrange a formula, and part of this is identifying what each unit is. You will always get 3 out of 4, okay? So you're only going to have one unknown in these. So you will know either P1, V1, and P2, then you got to find V2. Or you'll know P2, V2, and P1, you got to find V1. So you'll always know 3 of the 4. So here's the steps that I do in figuring them out. I read through the question and identify what does each unit mean. Okay, whenever you get to a number, you want to figure out what does it mean? What does it stand for? Then you may have to rearrange your formula so that the unknown is all by itself. Then you can just plug your numbers in. I rearrange the formula before I plug the numbers in so that I don't plug them in and then move them wrong. I just find it's easier to rearrange the formula. And again, this is always going to be multiplication and division, so significant figures from your measured numbers always come into play. So let's do one, and then we'll quit. So this one, a sample of gas changes from a volume of 82.3 liters. What's that? Liters is volume, right? So if you see liters, you know you've got volume. So now the question is this the initial volume or the final volume? Initial. So that's the initial. Can you read if a sample of gas changes from, so I know that this is my initial. It changes from 82.3 to 26.5 liters. So I know that is V2. So in reading, anytime you get to a number, identify what that unit represents. So what was the initial pressure? So now what's my unknown? So I want to find P1. And usually it'll be kind of in the second part of the sentence, either like the second half of the sentence or the second sentence. Look for like a what is, what will be, what was. Usually it'll like tell you that's your unknown. If the final pressure is 1825, so what's that? That is P2, right? Millimeters of mercury, that's a pressure. Atmospheres, that's a pressure. Those are your 2 possible pressure units that you'll see. If it's volume, it's always going to be liters. So you can, if you find it helpful, after doing the identification, you can list them. So P1, I don't know. V1, 82.3 liters. P2, 1,825 millimeters of mercury, mmHg. V2 is 26.5 liters. Okay? Just like as a way of identifying. These units. Practicing it this way will help like make sure that you don't flip them. Right? Because I've had students that like set everything up and then they put V1 in the V2 spot. They switch and I'm like, how did you get this number? And they're like, oh, that's what you did. Okay. So now if I want to find, so P1 times V1 equals P2 times V2. I want to find P1. That means I have to get P1 all by itself in the formula. So what do I have to move? Do you see I have to get V1 to the other side? So see, if I want, this is what I need, because that's my unknown. So whatever my unknown is, I need it all by itself on one side of my formula. So how do I move V1? Divide both sides by V1. So if I divide by V1, do you see that these units will cancel? Anything in doing the rearranging, if your unit you got to move is in the nominator in the top, when you move it to the other side, it'll always be in the denominator. So whenever you move, nominator goes to the denominator. If you have something in the denominator and you need to move it, it'll always end up in the nominator on the other side. Okay? So just sort of in checking yourself. So now I have my formula. So P1 equals P2 times V2 divided by V1. So now plug them in. Make sure you plug them in. Double check your numbers as you go. 1,825 mmHg times V2, which is 26.5 liters, divided by V1, which is 82.3 liters. Doing the math quickly in my head. I got 587 point. Well, let me try to write it so you can read it. 587.636695 liters and liters cancel. So this is mmHg. Okay, I just multiplied 1,825 times 26.5 divided by 82.3. I got 587.636695 mmHg. So 1, 2, 3, 4, 5, 6, 7, 8, 9 significant figures. Can I just leave it? No. So last step, once you get your answer, go back to your question, okay? 82.3, how many significant figures? 3. 26.5, 3. 1,825, 4. So that means that I got around to 3. Remember, the smallest number of significant figures in my problem, that tells me how to round. So when I go to round this, remember, just to review, start from the left, underline each significant figure. I got to keep the first 3. So 587, the next number, this would be a 6, so it's going to round up to 588. Okay? So we have this one, Boyle's Law, we're going to do Charles's Law, and then we're going to move on into intermolecular forces next time. So we should be able to get through the bulk of chapter 8, because after we get out of this, then we're going to talk about soap. We're going to talk about soap, and then we're going to talk about cell membranes, and that's pretty much it. This is really like the only math part of chapter 7. So all the rest of this stuff is really just theory. Okay?